This semester, Group 18 was tasked with designing a robot which scores goals under modified RoboCup small-size league rules. The RoboCup robotic soccer competition began in 1997, providing a standard problem through which to advance research in robotics challenges, including cooperative and dynamic planning, robot hardware, and computer vision. The robot competed in a 2-meter square field and scored into blue and yellow colored goals using an orange golf ball, while avoiding static opponents or obstacles. Full marks were awarded for scoring 2 goals per minute while avoiding multiple obstacles. The project was split up into drive, kicker and dribbler, vision, and navigation and AI subsystems, with one group member assigned to each.
Hi, my name is Sebastian and I'm the drive system engineer. A differential drive system was chosen due to its simplicity and ease of control. 2 DC motors with a nominal voltage of 6 volts and a gear ratio of 1:15:1 were selected. These motors were controlled with DRV833 motor controller. 2 wheels with a diameter of 42 mm were designed and 3D printed. Additional rubber bands were added, allowing better motion for the robot. A PCB was designed to power the drive motors, kicker, and dribbler. The DRV833 motor controller was selected as it can control 2 motors at a time. The PCB is also capable of stepping the 7.4 volt voltage from the battery to a 5 volts output for the Raspberry Pi. A voltage divider circuit was also implemented for the laser photoresistor feature, allowing the navigations to know when the ball was in the dribbler.
My name is Lachlan, and I was the design engineer responsible for the kicker and dribbler system of our robot. My preset goals for the dribbler was to be able to hold constant control over the ball, whether it's moving forwards, backwards, or turning on the spot. This was achieved through a 3D printed cylinder that was attached to a 50-to-1 gear motor. This would exert constant backspin on the ball to keep it within the dribbler. To conserve power, the dribbler would only activate when the IR sensor senses the ball. Grip was then provided by wrapping rubber bands around the cylinder. The goals for the kicker was to achieve a constant kick of speeds of up to 2 meters per second. The kick was created by a 36-volt push-pull linear solenoid. This is powered by stepping the voltage from the battery up via a boost converter, and they're controlled by a 5-volt relay. A solenoid was chosen over other designs, such as rack and pinion, for its simplicity and consistency.
Hi, my name is Therese and I'm the computer vision engineer for this project. The vision subsystem comprises of the 8-megapixel Pi camera mounted at the front of the robot, which enables the robot to take inputs from the field to identify and locate objects. The live video captured on the camera is converted into the HSV color space, and each object is thresholded using the maximum and minimum hue, saturation, and value. HSV was chosen because a hue channel separates the colors from lighting conditions. This enables the robot to segment the ball, goals, walls, and obstacles on the field. The geometry of the camera and the ratio between the object height and camera sensor height was used to determine the distance between the robot and the object. The bearing of the object can also be calculated by finding the ratio between the frame width and the object centroid along the camera's field of view. The distance and bearing of the objects on the field is integrated into the navigation system so the robot can make decisions about its movement.
I'm Jared, the navigation and AI engineer for the project. Range and bearing data from the vision system was fed into a state machine which made decisions and controlled the dribbler and kicker and drive systems. Firstly, the robot searches for the ball by spinning on the spot and then spins in a wider circle to see around obstacles. The robot then navigates to the ball until it trips a laser sensor and is captured by the dribbler. This sensor covered a blind spot from the vision system and ensured that the robot was always in the correct state. Navigation was primarily achieved with a reactive method using proportional controllers. An attractive controller turns and drives the robot toward the target, while repulsive controllers turn the robot away from each obstacle in view. This was used instead of a state-based world frame system because it was much more fault-tolerant in practice. A similar method to the ball search is used to find the goal and navigate toward it. When close to the goal, the robot kicks and scores. When integrated, these 4 subsystems formed a capable robot with advanced functionality. In testing, the final robot successfully avoided multiple obstacles and achieved a rate of 2 goals per minute.